Okay, so do you have any questions before we start? Okay, so yesterday we kind of made a very brief introduction to phase transitions. So like the solid and liquid, we discussed how we can study, for example, the vapor pressure if there is a solid vapor phase transition. Now today we will be going a bit more in detail, but not that much. This is, again, it will be a rather preliminary discussion of phase transitions. Hopefully we will come back to phase transition in more detail towards the end of the semester. Now, one of the most commonly known phase transition would be, for example, the water. We have the solid phase, liquid phase, and the gas phase. And our common experience is, for example, in one atmosphere, if you consider the pressure as a function of volume. Now, let's look at how the phases change as a function of the temperature. Well, in our everyday life, we are in one atmosphere. So if you look at this, the pressure of one atmosphere, below a given temperature, so up to this point, it is solid. Now, when the temperature reaches a given value, it melts, so we have a liquid up to another temperature. And after the liquid phase, we have the gas phase at a given pressure. Now, depending on the pressure, this behavior changes. So, for example, if you increase the pressure, so our common experience kind of tells us that the gas becomes, at a given temperature, the gas phase becomes liquid. Or if you lower the pressure, liquid becomes gas. At a given temperature, you are not changing the temperature. So let's say if you go to a higher temperature, higher pressure, you have to go to even higher temperatures to obtain the gas phase. And, well, more or less the same thing happens in the solid-liquid phase transition also. So the boiling point changes if you change the pressure. For example, the reason why the ice skaters can easily slide on ice is that since the slides are very narrow, they exert a huge pressure on ice. So that huge pressure at the same temperature causes ice to melt. So actually they are sliding on a very thin film of liquid at a very low temperature, at a very low friction. And this diagram usually looks like something like this. Now we will study these lines in slightly a bit more detail. So do they go up, do they go down, do they terminate? Well, let me erase this one. Now, for example, what is a differentiating property of the liquid and the gas? What would we say? How do you distinguish a gas from a liquid?
Particles are, let's say...
You see, when you look at something, how can you say that something is a gas or something is a liquid?
If particles are everywhere, then...
Well, just obtain a closed container filled with liquid, particles are everywhere.
Usually particles have more, let's say, force in between them when they are located.
How do you differentiate it? Yes, if you go to the microscopic picture, okay, so you can say that there are bones, etc. But how do you differentiate them? Without looking at the microscopic details. Which thermodynamic property can you use to differentiate them? Now, we are not interested in the extensive properties, but the intensive properties as, let's say, entropy per particle, volume per particle, pressure, temperature.
It's definitely entropy.
Why not volume? Why not volume? You see, I can change the entropy of a liquid so that it matches the entropy of a gas by just adding some heat, increasing the pressure, etc. It's usually the volume that differentiates, let's say, the water vapor from liquid water. But then there is a problem though. You see, volume per particle in an ideal gas. Now, for non-ideal gas, there will be some modifications. But for a gas, the volume per particle decreases with pressure. If you increase pressure, volume per particle decreases. Well, if you increase pressure sufficiently large, to sufficiently large values, the volume per particle of a liquid will become a volume per particle of a gas. And you were talking about bones. Well, since they were so close, they will be the same. There will be bones also in the gas. So practically, there will be no difference between a liquid and a gas. In that case, we don't really call it a gas or a liquid. But what it tells us is that, you see, there's a first order transition, let's say. So if we plot the let's say as a function of PV diagram, again, let's just look at the water in 1 atmosphere. Well, the solid has a very small volume. So at a given pressure, if the volume per particle is small enough, well, you are basically increasing the time, changing the temperature to control the volume per particle. So up to this point, you have the solid. But then the solid starts melting. During melting, the temperature is constant. So there is a region, the volume of my system is increasing because some particles are converting into a gas phase. But during this conversion, let's say, in this region, solid and liquid, they coexist. Well, after some volume, then it is completely liquid. Then again, after some volume, if you increase the volume per particle even further, well, the liquid starts evaporating. And when it starts evaporating, for a time, there is a joint, liquid and gas coexist until you reach some larger volume. At this point, all the liquid has evaporated, so you have a gas phase. So when the volume per particle increases even further, you have a gas phase. And again, okay, so you see these graphs, okay, so here, this is quite steep, typically. Here you have, I think this is more or less the shape. And these in the book it's called tie lines. are regions of coexistence where there are more than one phase in those regions. This is a typical phase diagram. So we have a PT and the PV phase diagram. So you see, above this pressure, well, it corresponds to this, not that one, sorry, somewhat above. At this point, that is called the critical point. And this is the critical pressure. This is the critical temperature, critical volume per particle. Again, here you have the critical pressure. Above that pressure, there is actually no distinction between liquid and gas. Now, the situation between, let's say, a solid and liquid or solid and gas is slightly different. You can always separate them, because whenever we talk about solids, what we actually mean are crystals. So, solid phase is basically a crystal. If you look at the water, when ice is a crystal. And the liquid gas to solid transition is actually a symmetry breaking transition. You see, liquids and gases have translational symmetry. On the average, the densities do not change from point to point because the particles are moving around. Whereas for the solids, well, there's no longer a translational symmetry. There's a discrete translational symmetry, a residual one. So it's a kind of a symmetry transition. And hence, whatever the temperature, pressure, etc. are, the symmetries either exist or they don't exist. So it's never a continuous transition. Now, such, let's say, rapid transitions are what's called a first-order transition. So you see, if you go from the liquid phase to the solid phase, or from the gas phase to the solid phase, or vice versa, there is a discontinuous change in certain thermodynamic properties, like the volume per particle. It changes discontinuously. The thermodynamic properties themselves are discontinuous. Here also, it's a first-order change from liquid to gas. But at this point, it's no longer a first-order change. The thermodynamic properties change continuously, but their higher-order derivatives will still change discontinuously. So that's what's called a second-order phase transition. Well, the names basically derive from whether the function itself is, the thermodynamic properties are discontinuous or not, or their higher derivatives are discontinuous or not. So if it itself is discontinuous, then it's a first-order transition. It's called a first-order transition. If the derivatives are discontinuous, I think historically, depending on which derivative was discontinuous, then you would give it a phase transition of such and such an order. But nowadays, all second-order phase transitions. And there's also a special point over here. That is called the tricritical point. That is TC, PC. In the PV diagram, it basically corresponds to this point. No, not C. T. Now, the nice thing about this tricritical point is that it is a single point. You see, the liquid-gas transition, the boiling, let's say, it happens at every temperature. It can happen at every temperature, let's say, depending on the pressure. But that tricritical point appears only at a particular pressure, particular volume per particle, and particular temperature, a fixed one. If I'm not wrong, it's for water. The tree critical temperature is 0.01 Celsius. So if you want to calibrate your equipment, well, you can either go to a calibration institute where they have all these equipments for calibration, or you can create the tree critical point. So wherever you are, you can create that point only at a particular temperature. So once you have that tree critical point where you have both liquid, gas, and solid, all three phases at the same time, then you know that the temperature is 0.01 degrees Celsius. It is fixed. And also keep in mind that this, the pressures over here, etc., are the pressures of the liquid. We are just assuming that we have just a single material, let's say. Now, what is boiling? What happens when something starts to boil? You see, if I would put a glass of water over here and come back in a couple of hours, I will see that the amount of water has decreased by a visible amount.
It's going to evaporate from the surface.
It evaporates. At every temperature, water evaporates.
When it's boiling, it evaporates from all over the world.
Exactly. So that's what separates boiling and this phase evaporation, let's say. Evaporation always happens. So when does it happen? So why does it suddenly start to evaporate at a given temperature? It starts evaporating everywhere. Let me write one more line over here. At 1 atmosphere, this line crosses 100 degrees Celsius. So you see, if you look at water, or any phase transition, any liquid if you like, as you said, water evaporates. Not only from the surface, also from inside. So suddenly, spontaneously, let's say, vapor bubble appears over there. If the temperature is below, you see, that is a phase transition. So you are basically along this line. If you are below 100 degrees, that phase transition happens at this pressure. Well, that pressure is lower than the atmospheric pressure. So if you look at over here, the pressure of the bubble is less than atmospheric pressure. If T is less than T boiling. But that means there is not enough force inside the bubble to keep the bubble from collapsing. So basically the bubble will collapse. So even if the bubble starts appearing, it will just condense immediately. So the only evaporation would happen through the surface. Because in the surface there won't be bubble formation. The water just evaporates and the gas just leaves away. But when you reach this temperature, you see this, when you reach this temperature, well, the pressure of the bubbles reaches the atmospheric pressure. Since it reaches the atmospheric pressure, once the bubble forms, it no longer collapses. It just starts moving to the top, expands, and so you have all these bubbles forming. You see, that's also why the boiling point changes with pressure. You see, if you go to a region where the pressure is higher than 1 atmosphere, the boiling point, you should reach this temperature for boiling to start. Or this is basically what's also happening in pressure boilers, düdüklü tencere. Since it's a confined environment, in fact, it never boils, because the more you increase the temperature, there will be more evaporation, meaning that the pressure inside will also increase. So the vapor pressure will never be above the atmospheric pressure. In fact, it will be exactly equal to the atmospheric pressure. Well, in that case, the atmospheric pressure itself is the vapor pressure. So you first wait for the air to escape the pressure boiler. So inside there's only the vapor pressure. And if you have noticed, do you ever use a pressure boiler, pressure cooker? So if you would just, without opening it, if you put it under the water, you will hear that it immediately starts boiling. Because you are lowering the temperature. By lowering the temperature, you are lowering the pressure of the gas inside, lower than the vapor pressure corresponding to the liquid at that temperature, because you didn't cool the liquid. Now the vapor pressure of the liquid is larger than the outside pressure, so it immediately starts boiling. Now there's, of course, one question we can ask. Well, how do we calculate these lines? Can we calculate them or relate them to some other properties? By the way, before going, you see, these are basically the objects that we see. Water has such a phase diagram. In the book you have the argon, which has a similar phase diagram. But if you go to, if you have some phase transitions at very low temperatures, then the phase transitions, their behavior also changes, because now you have quantum mechanical effects. Now, one interesting example would be the helium-4 and helium-3. You see, one of them is a fermion. Well, we haven't yet studied them in detail, but you have probably heard of. This is a fermion, and this is a boson. So what happens is, for example, if you take any of them above a given, let's say, temperature, it's liquid. Then here you have some, no, this is gas.
It's not going to be solid, right?
It's gas.
Mm-hmm.
Then you have the liquid. Somewhere over here you have a superfluid. And then here, above some pressure, you have the solid. So if it can be a solid, I think it was something like 25 atmospheres, but you have to increase the pressure to a very large value. Now in the case of helium-3, these transitions, the superfluid transition goes to, happens at even smaller temperatures. And if you want to create a solid, again you have to go to even higher pressures to be able to create a solid from helium-3, because being a fermion, it will try to avoid, the atoms, helium-3 atoms will try to avoid each other. And then what happens in helium-3 is more or less what happens in superconductivity. Fermions form Cooper pairs, and then they become a superfluid. So the mechanism also is completely different due to the quantum mechanical effects, which have to be taken into account. Now let's look at these graphs. So you see, the question is, how can we obtain the curves over here? How can we study them? These coexistence curves. You see, if you look at these diagrams, in the case of water, let's say at an arbitrary temperature, there is a pressure at which the liquid and gas coexist. So basically, if you would, if you can try, just take a syringe, put in some water, close the top with your finger, extend it. Basically, you are increasing the volume, lowering the pressure. But if you lower the pressure, you will see that it starts, if you do it fast enough, you will see that bubbles will be formed in the liquid. But it will be a very short period, so you have to be a bit careful. So if you just extend the syringe, you will see that bubbles will be formed. Well, when you release the syringe, then, okay, the volume will collapse a bit, but you will see that there will be some gas left. It's not because the air has leaked inside. It's basically when you were expanding it, water has evaporated, boiled in fact, at that temperature, because the atmospheric outside pressure will reduce it. It will boil and create some gas. And when you release it, well, the gas is still there. So it's the vapor. So you get boiling in room temperature. Now, if you have an example of this glass filled with water over here, okay, let's say we are in room temperature, there is an atmospheric pressure, there is a vapor pressure, so the vapor will start evaporating. If it will be a closed container, the vapor will evaporate until the vapor pressure inside the container will be equal to this pressure. Then, of course, there is the additional air, which also has its own pressure, etc., but it will not really affect the formation of the vapor. And once it reaches this pressure, everything will stop. But if the container is open, so the liquid will evaporate, and the water vapor will just leak out. So it will evaporate until all the liquid is evaporated, because it never comes to this coexistence pressure. Okay, let's go back to that line. You see, the coexistence of phases, let's say phase A and phase B, requires that the chemical potential of the phase A, let's say as a function of pressure and temperature, should be equal to the chemical potential of phase B. Now, what we are interested in is pressure as a function of the temperature. Along that line, along this line, what is the pressure as a function of temperature? So mu A Pt as a function of temperature at an arbitrary point along that line should be equal to mu B. Pressure now is a function of temperature and temperature. Well, let's just take the derivative with respect to temperature of both sides. Well, this will be the derivative of the chemical potential with respect to temperature plus at fixed pressure plus the derivative of the chemical potential with respect to pressure at constant temperature times the derivative of the pressure with respect to temperature. This should be equal to, well, the same thing for the B phase. Well, now we can determine how the pressure as a function of temperature changes with temperature. Just solve that equation for dP by dt. This will be equal to derivative of mu b with respect to temperature at constant pressure minus the derivative of mu a with respect to temperature at constant pressure divided by, let's see, derivative of mu a with respect to pressure at constant temperature minus derivative of mu b with respect to pressure at constant temperature. Now let's see, what are these derivatives? We had already derived what d mu was in terms of the entropy per particle and the volume per particle. Well, we had derived it yesterday. This one. Well, you see, the dP by dt is then derivative of the chemical potential with respect to temperature at constant pressure is nothing but the entropy per particle minus SA, SP, and plus SA divided by, well, the derivative of the chemical potential with respect to pressure is nothing but the volume per particle. So VA minus VB. SA minus SP divided by VA minus VB. Well, you see, in a phase transition, if you go back to this diagram, you see here we have at this point, let's say, oops, sorry, now this critical. If you look at this point, as you go from liquid to gas, the temperature is fixed. Temperature does not change in a phase transition. But the volume is changing, the system is constantly changing. So if you just, let's say, if you think in terms of the bonds, in a solid phase, the bonds are stronger than the liquid phase. In the liquid phase, they are still stronger than the gas phase. To break those bonds, you have to give energy to the system. Give some heat to the system. So that in a sense you are increasing the energy of the energy of the system to break those bonds. But if you give heat to the system, it doesn't cause a change in the temperature, so you just need to give some amount of heat per particle. Well, you see, the entropy difference, you see, the heat that you need to give will be basically some number L multiplied by, well, how much particle does change in the phase transition? You can say delta, let's say delta N. This is the latent heat. But then that means the change in the entropy is just L over T. Or the change in the entropy per particle is just L over T. Well, this tells me that dP by dt is L over T times delta V in the phase transition. This is what's called the Clausius-Clapeyron equation. Well, Clausius probably didn't know about statistical physics, by the way. But this is just, we derive this relation basically using thermodynamics. It's just the thermodynamic relationships. And in fact, you see, there is one thing peculiar about the water. You see, water, when it melts, its volume shrinks. Solid water has, solid H2O, let's say, solid water, so ice has a larger volume per particle than the liquid. That's why ice floats. If you create solids of benzene, for example, or other liquids that you can think of, they will just sink in their liquid. But water just floats. That's also one of the properties of water that makes life possible. So it's when it floats. Since it floats, it's a good isolator, the ice. So it prevents all the water from freezing in cold temperatures. But delta V has a different sign for water than for other materials. So this dP by dt curve for the liquid so if you go from solid to liquid, let's say, then L is positive, T is positive, delta V for water is negative, so this derivative is negative. So that curve, PT, coexistence curve for water, has a different slope than the coexistence curve, so this is solid, liquid, or gas, whichever one you like. For water has a different slope different meaning in sign than other materials. And the other properties, if you can determine L and delta V as a function of temperature, let's say, then you can actually determine this dP by dt, how this coexistence curve changes with temperature. And if you can measure one initial condition, one pressure temperature, then you can determine all the rest. Of course, this equation need not have a solution everywhere. You see, if you would try to apply that equation to the liquid gas phase, the existence of this critical point tells us that that equation does not have a solution for T larger than Tc. So if you can solve that equation, you will see that there's practically no solution after that point. The solution is only you can find a solution only up to that point. That kind of marks that critical point. Any questions? As I said, hopefully towards the end of the semester we will come back to this topic of phase transitions in somewhat more detail.
Is latent heat just a constant?
Of course, it depends on the temperature. It might have a small variation for large ranges of temperature. So you will find tables of latent heat for materials independent of temperature, but actually it depends on the temperature.
Because you said, can we see the phase transition graph again? PT diagram. If the temperature is below the critical temperature, you have to give the latent heat to liquid to make it a gas, right? But if there is it seems like you have a more efficient way in terms of energy if you just increase the temperature and make it gas. You can use a trick.
Well, you see, the question is if you are talking about the work that you need to do or the heat that you need to give, keep in mind that it depends on how you go from initial point to the final point. Okay. As you said, if you want to go from this point to this point, you can go along this line in which you will have a phase transition, or first order phase transition, where at least some of the thermodynamic properties will change discontinuously. Or you can also go along this line, where everything will change continuously. That's all fine. I mean, the change in the energy of your system will be the same. But the work that you have to do, the heat that you have to provide to the system, etc., they will all be different for different paths.
Then you have to do some work.
Sure.
Instead of giving heat.
I mean, the path, well, to be able to go along a particular path, you have to provide some particular form of heat, in a particular way, you have to do some work. You can choose your path so that you don't do any work, but you still need to give some heat. Or you can choose another path in which would require you to do both work and provide heat. But at the end of the day, the change in the energy will be the same. So you're not gaining energy actually. Any questions? Okay, let's give a break here. Then in the next hour we will start quantum statistics. Now at the end of the day we will see that basically whatever we did with classical systems we can actually do also in quantum systems without much modification, but to be conceptually correct there are some formalities we have to fill in. Okay, see you in the next hour.